All right, so I'm ready. I'm not sure if the audio crew is ready. Shall we get started? All right, so this is the official start. Welcome to this talk. Thanks for the people inviting me to come speak at your event. Sounds like a very nice opportunity to learn, to meet other people. I'm gonna talk about HTTPS. I'm gonna talk about some of the new things in HTTPS. I'm not going to talk about protocols and ciphers and all of these things. I'm going to talk about recent changes in the ecosystem. I'm going to talk about things that I think developers should know about what has changed in HTTPS. So to make sure that we're on the same page, let me quickly show you what happens on a very high level when an HTTPS connection is made. So essentially we have a browser and we have a server, and they want to talk securely. And to do that, they actually need a shared secret. So under the hood, they have some secret key that they both know, and they can use that to protect the traffic in between. Like I said, very high level, not a lot of details, so there's a lot more going on, but that's the general idea. To do that, they actually need another secret. They need to exchange this, they need to get that shared secret to both parties without revealing it. And to do that, they actually use this additional secret, which we know as a public key. It's a server's public key. But of course, we don't know who the server is, and we don't know whether we can trust it. So to make sure that that works, we have another step that happens there, and the browser essentially starts this handshake, it's called. It starts the setup, they exchange keys, and they set up the whole secure connection. But exchanging the key, you see the step here, the server tells the browser, yeah, sure, this is my key. But before the browser can trust that, we actually need a last thing in this image, and that's a certificate. And this shows you that the whole thing of getting the secure connection, there's a lot of work the browser needs to do to get there. And that is actually one of the tricky parts in HTTPS. The encryption and the integrity checking is actually not that hard. We have very good protocols. We have very good ciphers to make sure that that's secure. We have upgrades. We have future new versions coming out recently. So these things are actually not the tricky part, but the use of the certificate and getting this handshake done, that is the tricky part. And that's what I'm going to talk about today. I'm going to show you a few things that can go wrong. I'm going to show you what we should be doing today to make sure that they don't go wrong. Before we dive into details, a small word about myself. I'm Philippe De Ryck. I have a PhD in web security, and recently I started my own training business in web security training. It's called Pragmatic Web Security. So I've been doing training for quite a while, but it was time to start out on my own, which I did, and that's how I announced myself today. I'm also the organizer of the SecOpDev course, which is a week-long course on secure application development. So it's a course targeted towards developers with speakers from all over the world, in case you're interested in that. But let's talk about HTTPS. Let's talk about this thing in the browser, the HTTPS. You're very familiar with this. The UI changes every now and then, but under the hood, it's essentially what's happening there. We have a secure connection. We're loading everything securely, which is absolutely fundamental for modern web security. Of course, when you go to my website, you probably are not going to type https://pragmaticwebsecurity.com. No, you're very likely to type pragmaticwebsecurity.com and just go. And when you hit enter, the browser does some magic, and eventually he loads the secure version of the website. That's how a redirect works. That's how everybody serving HTTPS pages today actually solves the problem. But under the hood, if you look closely, well, if you would look at the network traffic that goes on, the browser actually, when you type in Pragmatic Web Security, it loads the HTTPS page, but the first request here is an HTTP request. It's an unsecure request going to the server, asking like, hey, can you serve me this page? And the server answers with this redirect, says like, oh no, location is HTTPS. You should go there if you want to get that content. Again, this is how everybody does it. But this is also a potential problem, because we're running on an untrusted network. Imagine being on the join network here. Somebody set it up, you have no idea who did, probably organizers, but could just as well be somebody with a device in his backpack pretending to be an insecure network. You connect to it and you go online. And all of this is sent over that network which you do not control and which the attacker might be able to manipulate traffic on. And one of the attacks that can happen there is known as SSL stripping. And SSL stripping, I have an example of how it works. So you have a browser of our victim. You have an untrusted network in between, which can be a Wi-Fi network. It can be your ISP. Plenty of parties have access to the network nowadays. And you have the legitimate application server. If you type in pragmaticwebsecurity.com, the browser is going to send this HTTP request. Remember, the network is untrusted, so the attacker can intercept that request, and he's going to forward that to the server. He's going to see, like, let's see what happens. And he sends a request to the server. The server is going to be like, no, I don't want HTTP, I want HTTPS. I'm going to upgrade with a redirect, and we're going to make sure that we have a secure connection here. The attacker intercepts all of that. The attacker is perfectly capable of setting up his own HTTPS connection. There's nothing preventing him from doing that. And what he does now in this attack is he actually rewrites the page. He strips the HTTPS from every URL, modifies the URLs, and sends that response back to the browser. So from the victim's point of view, we typed in pragmaticwebsecurity.com, and we got an HTML response from the attacker, but we don't know that. We got an HTML response, and we're happy. We see the web page. Yet, instead of running the HTTPS version, we're running the HTTP version, which is potentially a problem. And if the website would be more interesting than my website, you potentially could do something on there, like submit data. And whenever you do something, the attacker will still be in the middle because it's HTTP. The attacker has an unprotected traffic. He can easily read that. He forwards it. He can modify this in transit, so he can send something else to the server and again rewrite the response. So imagine if this would be an online bank, this would be very problematic because the attacker would be able to insert transactions and hide them in the response, and you would have no idea what you're doing except afterwards when the money is gone and you are essentially screwed. This is possible against 75 to 80% of websites nowadays because it is a design flaw. It's a problem in the way we set up this HTTPS connection. And every browser sends this HTTP request, and every browser or a lot of websites are vulnerable. Fortunately, we have a solution. We have a protection mechanism we can use to prevent this from happening, and that's known as strict transport security. And strict transport security, or HSTS for short, for HTTP strict transport security, is a response header that the server can send to the browser to tell the browser, like, I know you want to do this HTTPS conversion thing, but I'm telling you that I'm using HTTPS. So whenever you want to connect to me, don't try with HTTP first, because I want to use HTTPS. And this policy essentially tells the browser that for this period of time, for this max age in seconds, the browser should use HTTPS as a default communication mechanism. So no trying HTTP first, use HTTPS by default. This is in seconds, so the moment the browser sees this policy, this will be applied for the next year. So if you visit my website and I would set this policy, then for the next year, your browser remembers that my website uses HTTPS. And it's renewed every time it sees the header, so you can essentially continuously keep telling browsers that they should be using HTTPS by default. Side note, a year sounds long enough for most websites. It probably is. It kind of depends on the use case. One very good example is the Tax on Web website, which we all use once a year to file our taxes. If you are a week later this year and the policy has expired, then the browser will try HTTP by default again. So if you're building that website, you probably want to use a year and a half as the max age instead of a year. So you need to cover 2 subsequent visits of your users, and in some cases that might be a bit extreme. Has been around for a while. This policy is supported by all browsers and actually should be used by all HTTPS websites. As long as you're not serving an HTTP resource, as long as you're doing the default redirect on that domain, you should set this HSTS policy by default. That's unfortunately not something that very many people know, even though it's actually very easy to enable. You can take it a bit further. You can also add this flag called include subdomains, and it's kind of self-explanatory. The moment you set this on a specific domain, the browser will enforce this policy on all subdomains of that domain. So if you would set this on pragmaticwebsecurity.com, and next the user types in Angular masterclass.pragmaticwebsecurity.com, he would, because of this policy, use HTTPS by default. This is very powerful. This is very good, because this means that if you have a lot of subdomains, it's very easy to enable this setting on all of your subdomains, as long as the browser sees the parent domain. However, this also has the capability of disabling features on your subdomains. And very many people have a lot of stuff running on a subdomain. Like imagine you have your company websites, which is all HTTPS, everything is good there. But you have this very obscure intranet thing, like the management interface of a printer, and there's no HTTPS there. If you have it set up as printer1.whatevercompany.com, you enable this on your company.com domain, then that printer will become unreachable. And of course, if it's only a printer, it doesn't sound very dangerous, but a lot of intranet systems are still running on HTTP because it's intranet systems anyway, and security is maybe less important, which I don't agree with. But this thing actually has the capability to shoot yourself in the foot, so be careful with that. Reason I want to talk about why this is so dangerous is because you can take it, you can level up, you can go even further, and you can tell the browsers that by default your entire domain uses HTTPS. This is known as preloading. So the problem with HSTS is you need to send an HTTPS request first to get the policy and to know that it should be applied in the future. Meaning that the first time a user goes to your website, he doesn't know. The browser doesn't know to use HTTP or HTTPS. So we'll use HTTP. And with preloading, there's actually a hard-coded list of websites in your browser, in every browser today, that says these websites have alerted us that they only use HTTPS. You actually have to go to this website, hstspreload.org, and put yourself on the list. So you can ask them, please put me on the hard-coded list of browsers, and within 6 to 8 weeks you will be in the next release of Chrome or Safari or IE, well, Edge or whatever. Again, potentially very dangerous. Because if you do that, and all of a sudden something doesn't work, it's not very easy to disable this feature. Because you have to go back to the browsers and you have to essentially ask them very nicely, do you want to take my site off the list again because I screwed up and there is a problem? And they're probably going to be like, yeah, fine, we'll take you off. And then 6 to 8 weeks later, the problem will be fixed. So before you do this, I highly recommend running a policy without preloading for a very long time. It's very secure, except for that very first request, which is reduces the attack window quite a bit, and only then think about preloading. If you go to preloading immediately, things are gonna go wrong, as they have for quite a few people in the past as well. I have a few best practices throughout the talk. So this one is about HSTS, or HTTP strict transport security. This should be enabled. So if you're running HTTPS, everything should be running over HTTPS anyway. So it's actually once that is the case, it's very easy to enable this. You should do that with a decent max age. A year is the default recommended one. And you should work towards this include subdomains policy, which will take some time to figure out if you have covered everything, yes or no, and to see what happens there. Let's talk about, that's the setup. Let's talk about certificates. Let's talk about the one thing that actually makes sure that our HTTPS connection is secure. Because all of the other things depends on the fact whether the certificate presented by the server is legitimate. Again, an example from my website. This is one issued by Let's Encrypt. And you can see that the browser trusts this. He says, like, this certificate is valid. Meaning that the browser says somebody, Let's Encrypt in this case, vouched that Pragmatic Web Security is indeed the real party that requested this certificate. There's a few variations in types of validation. I'm not going to go into detail there. I'm going to talk about a little bit about the landscape, and then about a few serious problems that need to be addressed using, again, additional security mechanisms. Here's how the landscape works. So you have a certificate being issued by a certificate authority. Of course, certificate authorities, there's plenty of those available. It's a dynamic world, so they change as well. So instead of directly trusting a CA, each CA also has a certificate. And that certificate, again, is going to be signed by a different CA. So you get this hierarchy of CAs, each trusting each other, and eventually they are able to issue certificates. Because the top level one has, again, a certificate, and this keeps going until you reach like the highest level, and that's called the root CAs. And these root CAs are the ones trusted by the browser. And whenever the browser gets a certificate from a website, it will need to validate this whole chain to make sure that the certificate is actually valid. These are called intermediate CAs, and those are the certificates. And of course, the whole landscape is a lot more complex. This is not one CA with one certificate. This is, Let's Encrypt alone, for example, has issued about certificates for 70 million domains, I believe. So these things are huge. Everybody is using that. Everybody depends on this system, which is unfortunately not the best. Here's an overview of the list of certificate authorities in Firefox. So essentially, these root CAs are hard-coded in the browser. There's no other way to stop the chain from propagating, so eventually some of these root CAs are hard-coded in every browser or operating system, and these are the ones you trust. And because you trust these, you can trust these guys, and because you trust these guys, you can trust the certificate. Here's the list in Firefox. It's long, it just keeps going. I think there are about 200 different root CAs trusted by Firefox. If you would look closer, They come from everywhere. So you have some of them are a bit known. You have Komodo, which is a very well-known CA, but you also have stuff from Amazon in there. There's a lot. There's stuff from China, from all over the world, stuff from governments, stuff from private organizations, all of these trusted by default by the browser. Why is this a problem? Well, it used to work quite well, but today this is considered to be a bit problematic because any of these CAs can start issuing a certificate for a website that will be trusted by every browser. So for my website, they come from Let's Encrypt, but nothing stops a Chinese CA, or Amazon in this case, to issue a certificate from my website, and your browsers will accept it. And that's a problem, because sometimes things go wrong. Sometimes the CA is hacked. This is DigiNota. You may have heard about this. It's from the Netherlands from a couple of years ago, and this was a CA that got hacked real badly, as in they had full control, the attackers, over their systems. And they used that to issue certificates. A certificate for star.google.com. You can imagine that's a hell of a lot of power if you have a valid certificate for Google services. You can man in the middle everything and intercept all the traffic, read it, manipulate it, whatever you want. Governments have a bad reputation there. Sometimes they force a CA to issue a certificate. Sometimes they control a CA. They can easily issue a certificate. So these things are actually being abused in practice. It's a sophisticated attack, but these things actually happen. And when they happen, they're very hard to detect. They caught this by accident because somebody got a certificate error and it turned out that it was a Google certificate signed by DigiNota, and that tricked the Google team like, what's going on here? And that's how they discovered that the CA was actually hacked. So all of this whole ecosystem is based on this trust, yet today we don't have that trust anymore. We don't know whether we can trust the CA in China or whether we can trust the CA not to be compromised. And the reason that we have that system is because of historic reasons. And there's a video from 2011. It's quite old, but it's very entertaining, and I recommend watching it. It's a video from the OWASP dinner from the conference back then, and it's Moxie Marlinspike explaining how we got this CA ecosystem. And they actually called the guy that designed it. And it turns out that this whole CA and certificates was a bit of a hand wave because these attacks were theoretical. Somebody told them that, hey, you can intercept network traffic and then start messing with that, and they're like, oh yeah, we're going to fix it with certificates, and that's fine. And it was supposed to stop passive attacks, like somebody listening on the network traffic, and that is perfectly fine. That is what TLS does really well, or HTTPS does really well. But the moment somebody starts messing with the ecosystem and starts tricking CAs into generating certificates, the whole thing comes crumbling down. Of course, when it crumbles down, you have to apply some duct tape. So essentially, we have this whole historic system. We have all of this legacy, and it's very hard to just throw it out and say, like, we're going to build the whole new version of HTTPS with better approaches than the certificate system we have now, because it's not that easy to fix. So instead of having a by design fix, we actually have additional amendments to the current system. We have like new security mechanisms that we can add to make sure that we improve the system or prevent certain attacks from happening. I'm going to talk about 3 specific things that you can do or should do to further improve your HTTPS deployments. First thing, or the first item, is Certificate Authority Authorization, or CAA in short. And CAA is essentially a DNS record. So the spec allows you to specify these CAA DNS records, stating that for this domain, that is a valid CA. So this allows you, as an administrator or developer, to say, like, I'm only using these CAs. Additional to this DNS records, the requirement or the spec requires a CA to check these records before issuing a certificate. Meaning that, if I have set this up for my website and you try to trick a CA by exploiting a bug in their interface to issue a certificate for my domain, that CA should check my records, and if it's not listed in there, it will complain. It will say, like, sorry, I'm not a designated CA for pragmaticwebsecurity.com. I'm not going to issue a certificate for that domain. So it's not a silver bullet. It doesn't solve like the whole big problem. It solves one particular thing, and that's the mistakenly issuing a certificate to someone who shouldn't be getting it. And that, of course, only works if the CA is not fully compromised. If you have full control over the systems, you can bypass this. But unfortunately, CAs are also built on software. Software has bugs, and there are cases where you can trick a CA into issuing a certificate without fully compromising it, without compromising the backend systems. And then this thing will actually work. So it does reduce the attack surface just a little bit. And that's incremental steps, and that's how we get towards better security. So yes, you should be setting this up. Unless, of course, you require to work with like a huge amount of CAs, then this will probably not be very practical. But if you have one or two, then this actually does work very well, and this is highly recommended to set up. Also, very much recommended to set up a backup CA upfront. So you never know what's going to happen. You never know if a CA gets compromised and is taken offline. You never know if you get in a fight with your CA and you need to go somewhere else to get certificates. Well, if you have to start updating your DNS records first, that might be messy, so make sure you have that upfront. Make sure that you know if things go south, we can go there for an emergency certificate, and then we can fix our problems later on without breaking anything. That's, again, a best practice you should be following. The third, or the second system here, is also focusing on certificates. It's called certificate transparency. And this is a bit more complicated than the CA thing. It requires a lot more moving parts, but it's actually also quite powerful. Here's the idea behind certificate transparency. So the idea is that you have your admin or developer who manages the certificates in the application, and when you request a certificate from a CA, the CA will publish that certificate in a CT log, a certificate transparency log. And that log is just a list, a public list of issued certificates. That's part one of the picture. Part two is that the browser, eventually, Chrome already does this, other browsers will follow in the future, the browser will only start accepting certificates that have been published in a log. So it's essentially forcing CAs to publish certificates in a log, which is a good thing, because now we have a public list to see which certificates have been issued. And if the attacker would trick a CA into giving a certificate without logging it, the browser will reject it anyway. So this actually forces CAs to log it, but also if an attacker wants to get a fraudulent certificate, which browsers will accept, he will have to publish it. And that is a key requirement of certificate transparency. The name focuses on that publishing process, because the admin can now monitor these logs. I monitor the logs for pragmaticwebsecurity.com. And the moment a certificate is issued, I get an alert saying that, hey, there's a new certificate for this website issued by that CA. And if that comes from Let's Encrypt, I'm probably going to be, oh yeah, sure, everything's working correctly, that's good. If it comes from God knows where in China, I'm going to be like, help. And I'll have to figure out how to actually solve the problem. Because that again that's a different story, but that's also not that trivial. But this gives you the oversight. This gives people the oversight of fraudulent certificates being issued. So if somebody would hack DigiNota, if this is DigiNota, and they want a star.google.com certificate, if Chrome needs to accept it here, they need to publish it. And when it's published, Google will see that. And Google will immediately know that something is wrong, because they don't work with DigiNota, or didn't work with DigiNota, and they can start preventing that certificate from being abused in practice. Again, there's a lot more going on under the hood. There's a very complicated data structure to make it tamper-proof. There are timestamps for when the certificate was published and all of these things. But this is the idea. And actually, you don't need to worry about all of these underlying things, because they are handled automatically. For example, if you're using Let's Encrypt, the timestamps of when the certificate was published are embedded in the certificate. So you can see here, well, hopefully you can see it, that these certificates have been published in these logs, and the browser trusts these logs and knows that this is indeed okay. So Chrome will accept the certificate because it has been published. Well, it won't today because it's expired, but other than that, it would have it did accept it in the past. Again, CAs do this for you, so no need to worry about that. Browsers enforce this for you, no need to worry about that. The only thing you need to worry about is monitoring these logs, and there's tools for that. CAs are building their own tools, which they of course want to ask fees for. Facebook actually has a free one, which I use, which is actually quite good. It's a perfect excuse to use Facebook at work. It's for certificate monitoring, it's fine. Essentially, well, this is what you can query a domain. You can see all the certificates being issued. You can see who issued them, the issuer here. You can see how long they're valid and all of these things. And if you have the Facebook app, for example, I get alerts on my phone, hey, a new certificate has been issued, and I'm immediately in the loop to check whether this is legitimate, yes or no. very good best practice. Of course, there's one drawback about this, which honestly I'm not sure if they thought about upfront, but people thought about it after this was already deployed, and that is that all of your certificates are now public information. Meaning that if you have like obscure host names that nobody else knows exist except your developers, well, if you have HTTPS enabled on them, now everybody knows they exist. Here's an example from Bank of America. You see all of these very strange host names. I'm not sure, I haven't checked whether they're public or not. These could just as well be intranet services with a valid public certificate, but this leaks information. And actually people have started abusing this to discover uncompleted WordPress installs and Drupal installs. Because if you set up a website in these automated interfaces, you can click yes, enable HTTPS. It's going to request a certificate. It's going to leak your domain name, like supercoolblog.com. Somebody is going to go there before you have completed your installation procedure, and now they have taken over your Drupal website. So these things are being abused in practice as well, but just be aware that every certificate you request from a modern CA is public information. So there's no obscurity anymore, there's no hiding it, so keep that in mind. Best practice. So ensure that all certificates have CT information. So unless you have some really old certificates lying around, this should be the case. CAs have adopted this quietly over the past few years, so that's a good thing. And also make sure that you have a rigorous monitoring process. If you have teams following up on these things, make sure that they know about legitimate certificates, that they are able to catch the fact that a certificate might be generated fraudulently and needs to be revoked as soon as possible. Alright, leaves us with one more thing, and that is public key pinning. Here's the idea behind public key pinning. This is the most powerful security measure because it's a preventive one. The other ones were about detecting problems, especially CT, but public key pinning is about preventing a connection to be made if the certificate is not one we expect. Here's how it works. We have a client, we have a server, we have a list of valid key pins. So essentially the client has a list of these keys will be used by the server, or the server will use some of these, any one of these keys. Anything else than what's in the list should not be accepted. So whenever you make a connection, the server is going to send his public key with the certificate, of course, and the client will here make a decision, is this key in my whitelist, yes or no? If it is, it's going to be legitimate. If it isn't, that means that maybe somebody is intercepting my traffic and giving me a fraudulent certificate, something issued by some CA in China maybe, I don't know, but it's definitely not one of the keys I whitelisted. You may have noticed that I subtly changed the client. Instead of a browser, we have a phone here instead, so it's not a web client. And there's a very good reason for that, and that's because web browsers used to support public key pinning, but are moving away from public key pinning. And the reason that they're doing that is because it's really powerful, but also really fragile on the web. Because if you pin your public keys, it's very similar to strict transport security. You send your valid keys over as an HTTPS connection, and the browser stores them for a certain maximum age, like for a year, half a year, a month. But the moment you mess your pinning up, the moment you, well, essentially break the pins, the browser will no longer make an HTTPS connection because it says the pins are not valid. So when it doesn't make an HTTPS connection, you cannot update your pins because you have broken your connection and you need the connection to deliver new pins to the browser to fix the problem. And that is actually what's happening in practice. So one website, Smashing Magazine, enabled public key pinning, messed it up when they updated their certificate, and essentially took their entire website offline by messing up the pins. And they were able to restore it because they found a backup of their old key and got a new certificate with that key and made it work. But that was, they got very lucky. Otherwise, users would have been unable to access their website for a couple of months, which, as you can imagine, puts the website out of business. On the dark side of the story, instead of messing it up, attackers have been breaking into web servers, enabling this mechanism and taking away the key. So all of the users expect HTTPS with this particular key, but only the attacker has it now. So he's going to be like, well, if you pay me this much Bitcoin, I can give you the key so you can allow your users to visit your website again. And because of these stories, you should look it up. It's called ransom PKP. It's actually quite depressing how this can be abused. But this is the reason that browsers are moving away from this. It's too fragile on the web. But in my image, I had this mobile client. It actually works on mobile applications. And the reason it works on mobile applications or desktop applications or any other type of applications that's not the web is because you have a separate update channel. If you have a mobile application and if you should mess up your pins, you can use the App Store to push out an update that will fix the pinning problem. Because it's an out-of-band update channel. You don't need the pin channel to deliver new pins. And because of that, this actually works quite well. And it's actually, here's a code example. It's probably not very readable from back there. But essentially, it's a code example for Java, for Android, where you check a pin. So you, oh, sorry, that was not good. So you make a connection here, and essentially there's this function, validate pinning, which I haven't shown here, which will check if the checksum of the key, the fingerprint, is listed in this list of whitelisted keys. That's essentially what's going on. In a modern Android version, just to show you, you actually can do this from a config file. So you have this XML config where you can add your pins in the configuration file. So this is very easy to set up on Android and on similar platforms, and it's actually quite powerful. Because even if somebody has a legitimate certificate issued by a real CA that would be trusted by the browser, this connection will not be made because the pin will not be whitelisted. So the best practice here is stay away from key pinning in web applications. It's going to be deprecated in the browsers that did support it anyway, so there's no real need to work on that, and it's too fragile and too risky to actually use. But do use this for sensitive applications that have an out-of-band update channel. If you have a desktop application where people actually install updates from a different channel, you can actually use this, and you should use this, because it is really powerful, but only in the right scenarios. So let me wrap up. Essentially, HTTPS used to be enabling this mechanism, and you would be good to go. Very long time ago, you would have like mixed HTTP and HTTPS deployments. Today, you should have 100% HTTPS deployments. There shouldn't be parts of the website HTTP anymore. There's no good that will come of that. There's no real reason to do that. HTTPS is fast, HTTPS is cheap, HTTPS is easy to set up nowadays, so everything is HTTPS. If you don't believe me that it's fast and cheap, Netflix runs all the streaming over HTTPS. So if Netflix can run all their traffic over HTTPS, I'm pretty sure that your web applications can run their traffic over HTTPS as well. So there's no excuses anymore. You should have HSCS. If you are serving everything over HTTPS, setting this up is really, really easy. Start with a policy on one domain only, and then start checking and deploying this on every domain to make sure that you can have this include subdomains policy and potentially think about preloading. For me, preloading it's like the cherry on the pie. It's not a real strict requirement. It's something you should work towards, but it's not the first thing you should worry about. Deploying a good HSCS policy is more important. CAA, the Certificate Authority Authorization, DNS records to make sure that only a few CAs can issue certificates for your domain. That is highly recommended again. Should be fairly easy to set up. It's just a matter of configuring this. CT logs, also important. You need to log CT certificate transparency or monitor them to get information about new certificates. Keep in mind that everybody can do that. Nothing prevents someone from setting up monitoring on your domains, so make sure that you never leak information through there that shouldn't be seen. And then finally, public key pinning is very useful for applications with an out-of-band update channel, but shouldn't be used for web applications. In my last slide, I want to mention if you want to learn more about security, if you want to go deeper, I have 2 upcoming courses in October, one on Java-based web applications, which is about modern web security, and one on Angular. I'm not going to do more sales talk than that. That would be very nice. So the slides are available on my Twitter feed. If you want to grab a PDF of the slides, there's some additional slides in there with some more information on these mechanisms and what to do to actually deploy them. So grab a copy from there, and if you have any questions, we have 10 minutes left for questions, so we can do that here, or you can reach out to me later. You're welcome to do that. Thank you. Any questions? That was either really clear or really boring. All right, if there's no questions you want to ask publicly, that's fine. Thanks for being here, and I'll be here the rest of the day to chat about security things if you are interested in that as well. All right, thanks.